Okay, so let me just start by saying again that a solid is a lattice plus okay. So you have a sea of electrons, and it's the lattice that defines okay. So a solid is a combination of lattice plus electrons, and it's a lattice that always defines periodicity. Okay. Now, so if you look at the classical free electron model, which explains all the physical properties, the definitions of which we have seen, the electrical conductivity, thermal conductivity, Hall effect, and Wiedemann-Franz law. Most of these physical properties can be explained on the basis of the so-called classical free electron model. Okay. Now, the model also has been successful in most of these cases, especially in the case of explaining the electrical conduction properties of materials. There's no problem. And you also know that we have another property called the specific heat. Of course, when it comes to using the classical free electron model, the model does not consider a large number of interactions between electrons. Of course, the electron-electron interactions are considered, but the electron-phonon interactions are largely neglected. Okay. And the model also says that if you have certain number of atoms in a given volume, okay, which we can find easily in a given solid. So, and also depending on the number of electrons attached to each atom. Copper, for example, it has one valence electron. Sodium, and in some cases you have two valence electrons. So, all these electrons are supposed to participate, contribute to all these different physical properties. That means, if you are accounting for the property of electrical conduction, if you know the number of electrons or number of atoms in a given volume and the number of electrons attached to each atom, you will be able to evaluate a given property. Okay. So, that way you can get by theory and measurement the exact values. But then when it comes to, so it in one way considers electrons to be like gas molecules. So, the theories that are applied to the kinetic theory of gases is also applied to the free electron model. So, each electron having a kinetic energy of okay, right. But there are some problems. So, you have free electrons, there are not many interactions between electrons and other species, okay, and these are considered to be as free as gas molecules. Of course, then if you start accounting for the number density, and these number densities are of the order of 10 raised to 28 to 29 per meter cube. And typically, if you look at the number densities, in the case of a gas at NTP, these values are almost 3 orders less. That's how it goes. Okay. So, when it comes to, so electrons also contribute to the specific heat. We have defined what is specific heat. So, there is what is called the electronic specific heat. because the contribution to specific heat comes from both electrons and phonons. And if you are considering these free electrons, there is obviously a contribution from the electrons present in a solid. So, the theoretically calculated specific heat values, the electronic specific heat values are something like but when people started doing experiments to find the specific heat values, electronic specific heat values, these values turned out to be oh, you see the difference, almost 1 order difference between the theoretically predicted values of electronic specific heat and the experimentally obtained values. Then the questions came about, so what is the problem here, right? So, the classical theory of all electrons participating in a given process giving rise to the property of conduction, electrical conduction, thermal conduction, and a property called electronic specific heat. Is it that all the electrons are participating, or only few of them for some reason are participating in this process? So, that is where quantum mechanics so the initial theories were given by Drude or Drude. We have the well known point form of Ohm's law, from which the sigma value can be calculated. Similarly, you do a thermal conductivity measurement, you look at the validity of Weidemann, Franzela, etc., etc. Okay, it's no problem. So, in this particular case, when you are considering electrons as free particles, okay, obviously the Maxwell-Boltzmann statistics are used. Because we are considering electrons as free particles, right? Okay. And the real problem is this. So, we need to explain why there is a 1 order change between the theoretically predicted values and the experimental values. Okay. Now, let us see, let us start looking at the so called quantum mechanical corrections which are basically applied, still validating the basic the classical models. Okay. The classical model is still valid, but there are some quantum corrections applied to this the initial models in order to have a better understanding. So, what is quantum mechanics basically? Quantum mechanics basically deals with, so electron has both particle and wave nature, and typically quantum mechanics uses the electron wave function, you call it psi, okay, and what does psi do? Any idea? Okay. Before probability, what is the state of the system? It tells you, it gives you information about the state of the system, and it also gives you information about the probability of finding a particle. Okay. So, So, this probability of finding a particle, if it is 1, that means if the particle exists, its probability of getting found is 1 at a certain position. Okay. What else it does? In quantum mechanics, we also deal with operators operating on entities, right? So we call them quantum mechanical operators. There are several operators. You have the momentum operator, you can write it as a bold-faced letter, or you can write P with a cap on it. I can also represent it as Px, that means the momentum operator along the x-axis, which is the same along the y and z axis also. Okay, this is okay. So the quantum mechanical operator also deals with a Hamiltonian which is related to the total energy of the system. Okay, that's why when we are dealing with the energy operator, energy E, I can you have the time independent and time dependent okay. Now so you call it the energy Hamiltonian, time dependent part and the time independent equation. See, the basic quantity psi is finally used in writing down the well known the Schrodinger equation. Okay. Now, so the time independent one is nothing but you have the kinetic energy plus potential energy that gives rise to the total energy, and the time dependent case this is okay. So the Schrodinger equation basically describes, see, what the Newtonian mechanics and the conservation of energy that we learn in classical physics. Schrodinger equation deals with the same entities, quantities in quantum physics. So as simple as that. Okay. Now, V some potential. Now you call it operator OP. There is a momentum operator. I can write the kinetic energy part in terms of momentum, is it not? So in other words, the total energy term can be written in terms of kinetic energy and potential energy, and the kinetic energy term is written in terms of the momentum. And if you replace this momentum operator by this value, by that equation, you get the basic equation of Schrodinger in terms of two quantities expressed in slightly different way. So basically it's an energy conservation equation written in a quantum mechanical form. Okay. Now, there are two ways you can write a Schrodinger equation, a time dependent one and a time independent one. So, for simplicity, let us start with the time independent Schrodinger equation. It means what we are considering in this particular case is when the electron is propagating in a solid as a wave, right, we do not associate or take into consideration the extraneous perturbations that come in. That is where you need to apply the time dependent equation. So, for simplicity we can always start with the time independent Schrodinger equation. So, what is it? I have just written down again the time independent Schrodinger equation in the one dimensional case. We can always extend it to the 3 dimensions. So, H cross is H by 2 pi. This is called the reduced Planck's constant. M of course is the mass of the electron. See, the mass of the electron can apparently vary as it goes through the solid. That is why for all practical purposes there is nothing like a free electron. The electron is bound to the lattice in certain ways. So, as I told you, the electron, the periodicity of the solid is always defined by the lattice. So, the way the electron propagates in a lattice is in a solid is also defined by the lattice. So, strictly speaking, even though we talk about free electron theory, the electron is not so free to move. So, as it moves in the solid, it sort of experiences some kind of drag force which effectively changes the mass of the electron. This is the apparent change it is called. So, it is always appropriate to talk about the effective mass of an electron. We will come to this concept a little later. So, when you are talking about effective mass, we replace m by m star, right. Right. So, H cross is a Planck's constant, reduced Planck's constant, m is the mass, v is the potential energy of the particle at a given position defined by x. Okay. Now, I can also write a generic equation let me write it here again. Okay. What does this equation resemble? I have written it in this simple form using the Laplacian operator, where your del square psi is del square psi, dou square psi by dou x square, dou square psi by dou y square plus dou square psi by dou z square. Is it not? So, in 3-dimensional form you can replace all this by del square psi. It is called the Laplacian operator. So, this exactly resembles the equation of vibration, is it not? All right. Now, you can give several solutions to these Schrodinger equations. So, the most generic one is you can also write a solution in exponential form. Psi x is equal to a1 cos kx plus a2 sin kx. So, small k, we will come and see what k is. Okay. Now, of course, the probability of finding an electron so if there is a particle, the probability of finding it somewhere is always 1. Okay. Now I'll let us say the electron is moving in the solid, propagating the solid, and since we consider it as a free electron, it is not bound by anything. Okay. So this is not bound. So there are no boundary conditions to impose on the movement of the electron in a solid. Okay. That means the electron does not experience any potential at any point during its propagation in the solid. It means if I have a solid, if the electron is free to move from one end to the other end, right, your potential energy term should be 0. So we consider a completely free electron which is not bound by anything, it is not bound by any potential. So we get down to the equation now. What is this equation? This is a second order differential equation of an undamped vibration, right. So the wave is propagating and there is no potential, it does not undergo, there are no boundary conditions applied to the propagation of the wave. So you have continuous propagation of the wave. Okay. So it's a second order differential equation of a undamped wave. Okay. Now what is the generic solution again here? I can just the cos times sin terms also you can write it, but I am making it very simplified here. Okay. Now here k, what is k here? What is k? 2m by h cross square. Okay. Now k, of course, k is called wave vector. Why is it called a wave vector? Look, now Now, if I take the E kinetic energy, which is p square by 2m, your p square term becomes 2me. Now, if you replace that here, your k is it not? Which means, what is P? P is h by lambda, yeah? Your k is 2 pi by lambda, it is inversely proportional to the wavelength. So, it is associated with the wavelength of the propagation, of course, and it is called a vector because, as you can see, k is proportional to p momentum in turn is proportional to the velocity. Both momentum and velocity are vectors, so k is also a vector. That is why it is called a wave vector that defines the propagation of the electronic wave in the medium, which has really very important implications. What are the implications? Now, if you take this equation, okay, E is equal to h cross square k square by 2m. What does this equation tell you? Yes. So, this is y is equal to x square type of an equation. If you plot it, energy versus wave vector, which is something like that. So, in solid state physics, by the way, the classical model cannot distinguish between insulators and conductors, because even if the solid is insulating, you still have so many number of atoms per meter cube and so many electrons associated with each of these atoms. So, you should have contribution from the electrons attached to these atoms. So, that is a complication there. So, it really can't distinguish between conductors and insulators. Okay. Now, the EK diagram, it is called the EK diagram or the free electron parabola, plays a very vital role in explaining many things in solid state physics. Right. Before that, again, let me go back to the Schrodinger formalism. Okay. We talked about the probability of finding an electron in a system is obtained using the quantum mechanical principles. The important thing here is the quantum mechanical formalism always gives you what is called the expectation values. For you to understand it in a better way, if you look at the ground state electron orbit of the ground state electronic orbit ground state of hydrogen atom, well, immediately we give a value. We know that it's a magic number, 0.53 angstroms. We know we use it in physics all the time. This is nothing but your Bohr radius. So the classical physics allows you to give precise values like this. So when you say Bohr radius, it's 0.53 angstroms, right? So we take this value and use it freely, so no problem. Looking at the radius of the ground state hydrogen atom, always get what is called an expectation value. So if you do a set of good experiments to find out the radius, okay, the value can be, as an experimental physicist, if you have the setup to find out the radius in a very precise manner, however precise the experiment is, you still may get values more or less than this value. So quantum mechanics always tells you, well, this could be the most probable value. So you don't talk about the exact values always. That's why, you know, it gives what are called the expectation values. The expectation values, that the term that you come across in quantum mechanics is exactly this. There is nothing like exact, especially when you have an order of 10 raised to minus 11 meters, 0.53 angstroms. But for all practical purposes, you can take that value and use it for calculations. That's no problem. Where do we use Bohr radius? Again, this value plays a very important role. See, we no, we don't talk about reduction in dimensionality. We are just at the normal ground state. Say we deal with this in the macroscopic world. Where do you use it in the macroscopic world? Remember the free electrons, the term that we use it so loosely. Do we have free electrons in reality? If you have free electrons, where do you see them? So if I have say an electron source, and you can generate electrons by thermionic emission. You heat up a coil with by passing certain current, and electrons are emitted by the coil. And if these electrons are made to accelerate from the source to a point which is, say, 10 or 15 centimeters away in vacuum, right? So I see real free electrons. So you know the cathode ray tubes. In cathode ray tubes, you have electron generator. You can control the movement of electrons in the x and y directions, and you have real free electrons there. The electrons can move, you know, large distances. You know, in TV tubes, tube TVs, really 20-25 centimeters. But in solid, these electrons are not really free. Okay, they're never free, because I was telling you this. Tau is 10 to the power of minus 14 to minus 15 seconds. So in 1 second, the electron undergoes 10 to the power of 14 to 10 to the power of 15 collisions. It's always very busy going through multiple number of collisions. And of course, it's because of these collisions the resistive term comes. And then, so in reality, in a metal, in a conductor where you are supposed to have free electrons, right, the electron propagation will be there only when you have applied a field in a particular direction. So with this random motion, the electrons can drift in the direction or in the direction opposite to the electric field, depending on the charge of the carrier. So that's why we always talk about the drift velocity. Now you also have electrons in a semiconductor, or carriers, charge carriers in a semiconductor. So if I have a silicon doped with boron and phosphorus, in one case I make it into an n-type semiconductor where I bring in more number of electrons into the system. In the other case, you have more number of holes. Now the question always I ask is, so you are bringing more electrons into a semiconductor by making it say electron doped semiconductor, and you have free electrons, electron gas. So in metallic systems we don't talk about the presence of holes. It's always electrons, free electrons, right? There are always conduction electrons, plenty of them, and a large number, 10 to the power of 28 to 29 per meter cube. Now you can increase the electron density in a semiconductor by doping. So you are bringing in, so remember I gave you some numbers, the conductivity and can be changed by almost 4 to 5 orders. The electron density can also be changed by 3 to 4 to 5 orders. So are these also free electrons like in good conductors? Because see, if I have a phosphorus atom replacing a silicon atom, right? Phosphorus shares with 4 electrons of a silicon atom, and there is one excess electron coming from phosphorus, and that is free to move. Is that electron free to move? It's a free electron parabola, so it should, is it? So in that case, this electron should have the same property in terms of propagation in a lattice as the electron in a good conductor also. No, if electrons are majority carriers, you also have holes as minority carriers. So in an intrinsic semiconductor, you have n is equal to p, but if you are making it predominantly an n-type semiconductor, electrons are majority carriers and holes will be minority carriers, and the electron density could be increased by doping. What I am asking is, if the electron density is increased by 3 orders by doping, the excess electrons that are brought into the system, would they behave like the electrons in a normal conductor? Why? Because see, if the number density is more, the number of collisions also will be more. See, so in semiconductors you have 10 raised to 18 to 10 raised to 19 per centimeter cube. It is 3 orders more in the case of good conductors. So more number of the electron density is more collisions. So the electron density, if it is less, there should be less number of collisions. But that's a different issue. The way conduction changes as a function of temperature itself is different in both the cases. You know that, right? We can plot it and show. Remember that? Okay. Now the question is, if I am bringing an electron into a semiconductor, how free is this electron? Okay, the question is of course related to the Bohr radius. That's why I brought in this concept. This electron is not as free as an electron in a metallic system. The electron that you have in, say, a good conductor like silver, gold, platinum, which is supposed to be free electron, that means it doesn't belong to a particular atom. Okay? Now, the electron that is generated during the process of doping in a semiconductor is also free to move, but within a certain radius. This is very important. And how do you define that radius? The radius is defined by the Bohr radius times the dielectric constant of the material. So, it is a Bohr radius, dielectric constant is epsilon r multiplied by the, if the dielectric constant of a semiconductor is say 10, okay. Okay. Now, if you get this radius in 3-dimensional form, you extend it to a 3-dimensional sphere, what will be the value? This so what will be the radius if you have a spherical particle or spherical a sphere of radius in which this electron is free to propagate. So, the electron in a semiconductor is free to propagate only within that particular radius, not beyond that. Okay, now I have a well defined radius which is coming because of the Bohr radius times the dielectric constant or relative permittivity, and if this value is say 5 angstroms, I can calculate the 3-dimensional volume in which the electron is free to propagate. But then the issue here is, so I have a 3-dimensional radius, 3-dimensional sphere in which the electron is free to propagate, the another 3-dimensional sphere in which the other electron is free to propagate. Unless there is percolation between these different spheres, overall conduction will never happen. All these spheres have to percolate, their surfaces have to touch at some point, otherwise the conduction becomes only localized. You do not see the so called overall propagation. Okay? All right. Now, so what is the implication of this this particular EK diagram? H cross square k square by 2m. So, the electron can take all energy values, okay, in the so called K space, and you can also three-dimensional form of this equation. Okay, the kx, ky, kz are the wave vector components along the x, y, z directions. That means if you look at the electronic energy states in the 3-dimensional case, right, the electrons occupy a sphere, okay, with the topmost energy attained on the surface of the sphere. So, the surface of the sphere, so you almost see what is called energy continuum. Okay. So, in the 3-dimensional case, you have a sphere. The surface of the sphere is called the Fermi sphere. The sphere is called the Fermi sphere. The surface of the sphere is called the Fermi surface. Very important role. It plays an extremely important role in condensed matter physics, in solid state physics, in determining the any idea about this Fermi surface? So, the sphere that is defined in this way is called the Fermi sphere, and the surface of this sphere is called the Fermi surface. So, there is an energy associated with this surface which is called the Fermi energy. What is the significance of Fermi energy? Okay. What is the significance? Is it the Fermi energy is a small number or a large number? In a solid, when we talk about Fermi energy of a given element or a solid, is it a small value or a large number? So, we will see the significance of this, and we will also see what happens to this energy continuum when the electron is restricted by potential barriers, which does happen when electron is propagating in a solid. It is not free to move, and it is defined by the periodic potentials defined by the lattice, and how this periodic potential influences the energy continuum we will see in the next class.